This section we're going over limits at infinity and horizontal asymptotes. So first, let's start by taking a look at this function f of x equals x squared minus 1 over x squared plus 1. If we graphed it, it would look like this graph shown right here. And what we can see here is that there is a horizontal asymptote at y equals 1. And we can also see that as x is getting larger and larger and larger, which means more to the right on the graph, the y values are approaching this horizontal asymptote at y equals 1. So if we were writing this using limits, we would write it as the limit of that function as x goes to infinity equals 1. So just notice this section we're going to be looking at as x goes to infinity and also as x goes to negative infinity. Okay, so this right here represents the horizontal asymptote y equals 1. Okay, so in general, we use this notation. The limit of f of x as x goes to infinity equals L, where L is the limit, or the horizontal asymptote. So here are a couple more examples down here with limits as x goes to infinity equaling a number. So we can see in the first function, it is approaching the horizontal asymptote L. Same thing with the second function, and same thing with this last function. So the last function is a little bit different because it's oscillating, but it's getting closer and closer and closer as x goes to infinity. Okay, so let's take a look back at that graph of f of x from the previous page. Now we're going to look as x goes to negative infinity. So as x goes to negative infinity, that means we're moving more and more left on the x-axis, and just like as x goes to positive infinity for this graph, we can see that the function is approaching 1 again. So this doesn't always happen. Just because it's approaching 1 on the right doesn't mean it's approaching 1 on the left. In this case it was. And for symbolically, the way that we would represent it is the limit of the function as x goes to negative infinity equals 1. So once again, this 1 is because of the horizontal asymptote, and this time we are going towards negative infinity, which means more and more to the left when we're looking at the graph. Okay, so here's the generic notation, pretty much the same as before. And then here is the couple examples of it. So the limit of f of x as x goes to negative infinity. We can see it as we go more to the left. On that first graph, it's approaching that L. Same thing with the second graph. It is also approaching that L. So what that means is it's going to get asymptotically close to it. It's going to get closer and closer and closer to that value, but it's never actually going to touch it. Okay, and then also I just wrote at the bottom of this page, it's important to note that negative and positive infinity do not represent numbers. All right, now here we have just kind of the generic notation just so we have it all in one spot. So we have the first one, limit of f of x as x goes to infinity, and we can read that the way that I've been reading it. It also can be read as the limit of f of x as x increases without bound. So anytime you see the phrase without bound, that means essentially it's going towards infinity. Okay, and then we also have the other notation as x goes to negative infinity of f of x, and we could read this one once again as it decreases without bound. So infinity is increasing without bound, and negative infinity is decreasing without bound. Okay, let's see an example here. So let's find the limit of tangent inverse as x goes to negative infinity and as x goes to positive infinity. So taking a look as x approaches the negative infinity first, so we actually have it graphed for us right here, the inverse of tangent, and we can see that as x goes to negative infinity, it looks like the y values are approaching this horizontal tangent line, which is at negative pi over 2. So that's going to be negative pi over 2. So that means as x gets more and more negative all the way to the left when we're looking at the graph, that means the function values are going to be getting closer and closer to negative pi over 2. Now let's take a look as x goes to positive infinity. So as x goes to positive infinity, there's our function. It looks like it's approaching that horizontal tangent line at pi over 2. So that's going to equal pi over 2. So as x gets more and more positive, as it increases without bound, the y values for this function are going to get closer and closer to pi over 2. Next, let's take a look at the limit of 1 over x as x approaches negative and positive infinity. So let's take a look at negative infinity first as x approaches negative infinity. And I have the graph down below here, but before we take a look at it, let's make a little table. So I made an XY table where x are these x values that I chose, and then f of x is the function 1 over x. Notice these x values that I chose are getting more and more negative. They're approaching negative infinity. Okay, so let's go ahead and plug them in the function. If we plug them in, it's 1 over x. So 1 over negative 1 is negative 1. 1 over negative 10 is negative 1/10, which is negative 0.1. And then we have negative 1 over 100, which is negative 0.01. Negative 1 over 1,000, which is negative 0.001. We could keep on going. We could have chosen larger numbers here, but hopefully it's kind of clear here that these numbers are approaching 0. So we have our x values approaching negative infinity, and the function values are approaching 0. Okay, let's go ahead and do the other one now. We'll take a look at the limit as x goes to positive infinity of 1 over x. And let's make a little table again. And I'm choosing essentially the same values for x that I'm going to plug in, except they're going to be positive. So I'm choosing values that are bigger and bigger, which means x is going towards infinity. And let's plug them in. So 1 over x, that's 1 over 1. And then 1 over 10, 1 over 100, 1 over 1,000. And you can write those as decimals like I just did before. And you would see that these values are getting smaller and smaller, which means they're going towards 0. If you have a fraction and the numerator stays the same and the denominator is getting bigger, that means in general, it's going towards 0. Okay, so this is also going to be 0 for this limit. And if we had the graph graphed for us, or if we graphed it ourselves, we would see it looked like this. As it goes to negative infinity, it's going towards 0. Positive infinity, it's also going towards 0. So next thing here, we have a theorem. So this theorem is pretty important. The theorem says that if r is a positive rational number, so r is a positive rational number, then the limit of 1 over x to the r power as x goes to infinity equals 0. So I'm just going to throw in an easy example. Let's say x is going to infinity for 1 over x squared. That's going to equal 0 because our r value here is 2, and 2 is greater than 0, so r greater than 0. Okay, so that means as x is getting larger and larger, 1 over x squared is going towards 0. Should make sense because that denominator is going to get huge very quickly, and if that denominator is getting big, the number as a whole is getting smaller. Okay, and then the same thing can be said as x goes to negative infinity. 1 over x to the r is going to approach 0. So let's see an example here and how we tackle these harder ones. Let's say we want to evaluate the limit as x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. So notice we can't just skip to using this theorem that we just learned right away because it's not written in that form. So what we have to know to do if we're given a nice little, in this case, rational expression, we have to divide every term in the numerator and denominator by the highest degree in the denominator. So this is what we're going to do every time we see a problem like this. So the highest degree in the denominator here, is x squared. So the way that I kind of write it is I do divided by x squared, divided by x squared. You're doing it in the numerator and denominator. And then I skip to writing it where every term gets divided by x squared. So first we have 3x squared divided by x squared. That's just 3. And then we have negative x, so just minus, and then x divided by x squared is 1 over x, right? X over x squared, one of the x's cancels, we're left with 1 over x. And then we have minus 2 over x squared, nothing cancels, so we leave it just like that. So that is the whole numerator. Let's take a look at the denominator. 5x squared divided by x squared is 5. And then we have 4x divided by x squared is 4 over x. And then we have 1 over x squared, so just 1 over x squared. Okay, so that looks like we made it more complicated, but now we're going to use limit laws, and we're going to give each one of these terms, well, let's do the numerator and denominator first, and then we'll do that. So we're going to do the limit of the numerator. So remember, this is just limit laws from several sections ago, divided by the limit of the denominator. And we're going to see that we actually don't have to write this out every single time, but it's good to know that this is what we're actually doing. And then lastly, for limit laws, we're going to give the limit to each one of these terms individually. So we're going to be taking the limit of 3 minus the limit of 1 over x minus the limit of 2 over x squared for the numerator, and then the denominator looks similar, and it looks something like that. Just be careful, make sure that there's subtraction where there should be. And now we can use our easier kind of limit laws in the rule that we just learned, and we can say that the limit, we have the limit as x approaches infinity for 3, that's just going to be equal to 3. And then we have minus the limit as x goes to infinity of 1 over x. We just learned that this was 0 because that's 1 over x to the first, and 1 is a positive number, so that's going to be 0. So minus 0, which we obviously don't have to write. I'm not going to write it, actually. Same thing with this next one. 2 over x squared as x goes to infinity, that's also going to be 0 because what we just learned at the top of this page. And if we really wanted to, we could have taken this 2 and written it out front. 2 times 0 is still 0. Okay, so all we have in the numerator is 3. Denominator, we have the limit as x approaches infinity for 5, which is 5. And then we have 4 over x as x approaches infinity, that's going to be 0. And then 1 over x squared, once again, is 0. Okay, so this actually just equals 3/5, and that is our answer. Okay, so notice how we kind of could have skipped some steps here and probably just figured out the answer from this first step. That is completely fine. We could have said, okay, that's equal to 3/5, because we know that these 4 are all going to be 0. All right, and then we also just put the graph here just so we can take a look at the graph. 3/5 is the same as 0.6. Okay, it's important to know that this is only the case when x is going to infinity or negative infinity. Okay, next question. Find the horizontal and vertical asymptotes of this function. Let's start with the horizontal asymptote. We need to do two things. We need to do the limit as x goes to infinity and the limit as x goes to negative infinity. So let's do positive infinity first. So this is going to be similar to what we just did. We have to divide everything in the numerator and denominator by the highest degree in the denominator. It's pretty obvious that the highest degree in the denominator is just x. So when we're dividing by x, the denominator is pretty simple, right? Because we have 3x over x, which is 3, minus 5 over x, which is x, or 5 over x. The numerator is a little bit harder, so I'm just going to push this on the side here. So when we're doing radical 2x squared plus 1 divided by x, we can't just go ahead and combine everything because the numerator has a square root and this denominator has just an x. What we have to do is rewrite it using the fact that the square root of x squared equals x. So x equals the square root of x squared, right? Square root and the squared cancel. So what this becomes is the square root of 2x squared plus 1 over the square root of x squared. And now we can go ahead and combine those into 1. That's 2x squared plus 1 over x squared. And now we can divide both of those terms by x squared, and we get 2 plus 1 over x squared. So that's what the numerator becomes for right here. So that's kind of the hard part for these questions. You have to rewrite the highest degree in the denominator, taking into account there was a square root in the numerator. Okay, and then we're going to go ahead and use limit laws. Hopefully we don't have to, put it in the numerator, put it in the denominator, and take like 3 steps to do this. Hopefully we can see that this term right here is going to be 0 because the limit as x goes to infinity of 1 over x squared. Similarly, this one right here, 5 over x, as x goes to infinity is going to be 0. We're going to be left with radical 2 over 3 because those are just constants, and that's going to be our answer. So since that is our answer, that's going to be the horizontal asymptote. Okay, now let's do the limit as x goes to negative infinity of the function. But when we are dividing the numerator and denominator by x for this time, we have a little bit of an issue. And that issue comes in the numerator. When x is negative, the square root of x squared has to equal negative x. So that's because if you have something like x equals negative 2, you can't just simply say that's the same thing as x square root of x squared, because if you try to do the square root of negative 2 squared, that would give you the square root of positive 4, which is 2, which is wrong. So since we have negative square root of x squared, if we use negative 2, that would give us negative square root of 4, so now it would be, negative 2, so now it would be correct. So all this means is if you're doing a question like this with the square root, and you're dividing by, as x goes to negative infinity here, you have to keep this in mind, and you have to use the negative version of it. So what we have to do is divide by negative square root of x squared. So we end up with something almost identical to the first one that we did, except for this negative here, because we're going towards negative infinity, and we're dealing with square root of x squared. Okay, so I'm going to go a little bit faster for this little part here. That's going to be the limit as x goes to negative infinity. That numerator ends up being the same thing, except it's going to be negative. So we get negative square root of 2 plus 1 over x squared. Once again, same thing that we just did in the other one, so that's why I skipped writing it out. In that denominator, same thing as the other one. We can see that we're going to be getting essentially the same exact thing, but a negative answer. Negative square root of 2 over 3. So we just found our horizontal asymptotes are plus or minus radical 2 over 3, which you can actually see here in the graph. So let's do the vertical asymptote. So we know there's going to be a vertical asymptote when the denominator equals 0. And that denominator was 3x minus 5. when we set that equal to 0, we end up getting x equals 5 over 3. And technically what you should be doing is you should be checking that the limit, checking what's happening to the right and to the left of it. The limit as we approach 5 over 3 from the right of our function, if we made a table of values and x is getting closer to 5/3, we would see that this would be approaching infinity. And then similarly, as we approach 5/3 from the left, we would see that this equals negative infinity. So the infinity answers tell us a vertical asymptote, and then as x approaches infinity or negative infinity, that would be the horizontal asymptote. So we can see the vertical asymptote in this graph right up here also. Here it is right here. Next example, we want to compute the limit as x goes to infinity of the square root of x squared plus 1 minus x. So notice that we can't just plug in infinity, right? Let's pretend like we tried to just to see what happened. That would be infinity squared plus 1 minus infinity. It's kind of hard to see what is happening here, right? Infinity squared is infinity, plus 1 is still infinity. The square root of infinity is still a version of infinity. So we're left with kind of infinity minus infinity. That doesn't tell us anything, so we cannot do that method at all. So what we're going to do is actually rewrite this in a way where we can use the rule that we just learned. And that's going to be multiply by the conjugate. So the conjugate of the square root of x squared plus 1 minus x is the square root of x plus 1 plus x. Remember, conjugates, same two terms, one's addition, one is subtraction. So we're going to multiply this by the square root of x squared plus 1 plus x. And then we also have to do it in the denominator, so we're not changing anything. Okay, so this is one of the tricky problems where you just have to know to do this. And kind of the hint is because it's not in the form that we know how to handle. And then there's these two terms where one of them is the square root. So the numerator, when multiplying conjugates, remember it's a squared minus b squared equals a plus b times a minus b, the opposite of difference of squares factoring. It's going to be the first one squared. So the square root squared, they cancel. You're just left with x squared plus 1, minus the second one squared. The second one squared is x squared, so it's minus x squared. Let me just write that up here just so we remember that. Conjugates being multiplied. A plus b times a minus b. Shortcut is a squared minus b squared. That's all I did in the numerator. So the denominator is going to be just this whole denominator right here, which is the square root of x squared plus 1 plus x. Okay, so hopefully we recognize that that numerator can simplify, which is great. We're just left with a 1 in the numerator, divided by this whole nasty denominator still. Now we kind of have two options here. We could divide by the highest degree in the denominator, which would be x, and we could do that and see what happened, but we would have to divide this by x, this by the square root of x squared, and then this by x. You can do that. Maybe go ahead and practice that, see what happens. Let's think about this one logically. As x goes to infinity, the numerator is going to stay at 1, right? Because it's just constant, it's a 1. For the denominator, as x goes to infinity, that denominator is also going to go towards infinity. Because it's essentially the square root of infinity, which is infinity plus infinity. No matter what we do with these x values, as long as they're getting larger and larger, that expression as a whole is going to be getting larger and larger. So that's kind of going to be like 1 over infinity, which tells us this would be 0. So this was a good example of being able to kind of logic your way through it, which you can do sometimes, and just kind of try to write a little explanation like that. Okay, and then here's a little graph. If you want to take a look at it, x goes to infinity. The function's going towards 0. Okay, the next thing we got here is the graph of the natural exponential function y equals e to the x. We know it has a horizontal asymptote at y equals 0, and the important thing is boxed in. The limit as x goes to negative infinity of e to the x equals 0. So it's obvious when we have the graph, right? Because we can just say as x goes to negative infinity, clearly that function is approaching that horizontal asymptote at y equals 0. Thinking about it kind of logically again, no, you should never plug in infinity, but let's pretend like we did. As x goes to negative infinity of e to the x, that would be like e to the negative infinity, right? If we rewrote that, making it a positive exponent, that's 1 over e to the infinity, which e to the infinity is definitely infinity again. So that's 1 over infinity, which would be 0. 1 over something huge, it's going to be 0. Once again, never actually plug that in. Don't do this. This is bad. But if it helps you just kind of write it on the side to see what's happening, that's fine. Just don't keep it as your work because it's actually not mathematically correct to write that. Okay, so let's see some examples. We have the limit of g of x as x goes to negative infinity, where g is 1 plus e to the x. Let's go ahead and we obviously have the graph right here. Let's do it without the graph. Limit as x goes to negative infinity of 1 plus e to the x. So using limit laws, we're going to do the limit as x goes to negative infinity of 1 plus the limit as x goes to negative infinity of e to the x. So obviously the first one is 1, the limit of 1, it's a constant. And then this one is 0 because of what we just said right at the top of the page. So this is 1 plus 0, so just 1, so that is our answer. And then you can see that the graph verifies it. It looks like it's approaching a value of y equals 1. Next example, we want to find the limit of sine of x as x goes to infinity. Okay, so for this one, once again, we can't just take infinity and plug it in. It's not a number, so we cannot do that. Let's think about the graph. We know sine looks something like this, where it goes down, it has a range of -1 to +1, and then it oscillates, cuts through the origin, maximum at pi over 2, cuts through at pi, minimum at 3 pi over 2, cuts through at 2 pi, and then it repeats over and over again, and it does the same thing over here in the negative x's. But we are interested in what's happening as x goes towards infinity. So we want to know what's happening all the way to the right. Is the function settling down and approaching a single number? And the answer is no, right? Because this is just going to keep on oscillating over and over again infinitely, and it's never going to stop. So since that happens, and since it doesn't approach an actual value, we say the limit does not exist. Okay, so not everything will have a horizontal asymptote, obviously. Okay, so this is the last concept here with several examples. We have limits at infinity. So this is going to be when we are taking the limit as x goes to positive or negative infinity, and then we can also get an answer being positive or negative infinity. So let's do a couple examples. Let's find the limit of x cubed as x goes to plus or minus infinity. We should know what the function y equals x cubed looks like. We should be able to visualize it and graph it pretty quickly. It looks something like this. So we can very clearly kind of see what's happening here as x goes to, let's take a look at x goes to infinity first. So the limit as x goes to positive infinity of x cubed. If we are going further and further to the right, this function's blowing up, right? It's increasing without bound. So that means this answer is going to be infinity. Then we can also take a look as the limit as x approaches negative infinity. So as we go more and more to the left, the function is going really far down. It is decreasing without bound, so that answer is going to be negative infinity. And just to verify, you could also make a table of values and say, well, as x goes to infinity, we can say, let's use x as 10. That would be 1,000. Let's use x as 100. And that would be 1 million. We can use x as 1,000. And that would be 1 billion. And you can keep on going, and you can see that that's going towards infinity. And then you can do it the other way too and say negative 10 cubed, negative 100 cubed as x goes to negative infinity, negative 1,000 cubed, and they're going to equal the same numbers except negative, which shows us that it's going towards negative infinity for that one. Okay, a couple more examples. We want to find the limit of e to the x as x approaches infinity. So this one should be pretty obvious that this answer is going to be infinity, right? Because if you're plugging in values of x that are getting larger and larger, e to the x is going to blow up super fast, like e to the 10, e to the 100, e to the 1,000, e to the 1 million. That number is going to go towards infinity a lot quicker than x does, actually. And also, we should know what the graph looks like. The graph looks something like this. And you can see that the function values are blowing up, increasing without bound as x goes to infinity. Okay, next one we have the limit as x goes to infinity of x squared minus x. So it is important to note that this you cannot plug in like we mentioned earlier. It doesn't equal infinity squared, which would be infinity, minus infinity. So don't write that. So it's important to note that that is not the case. So what we can write, which may be a little bit less obvious here, is we can write this as the limit of x times x minus 1. All we did was factor out an x using GCF. So this is kind of like saying, once again, we cannot plug in infinity, but let's say we could plug in infinity. That would be infinity times infinity minus 1. Infinity minus 1 would still be infinity. Infinity times infinity would still be infinity, which that kind of tells us the answer. But for the millionth time, you can't actually write that. So we would write that the answer is infinity. And that's because x and x minus 1 both increase without bound as x goes to infinity. And if we multiply that together, then their product will as well. That's essentially using limit laws, but not really writing it out because we're working with infinity, just kind of logically explaining it. Last example, we want to find the limit as x goes to infinity of x squared plus x over 3 minus x. So we're going to divide everything by the highest degree in the denominator, which in this case is x. So dividing the numerator by x and dividing every term by x, x squared divided by x is x, and then x divided by x is 1. So we're left with x plus 1 in the numerator. Denominator, 3 divided by x is 3 over x, and then x over x is 1. Okay, so now we can go ahead and take a look at the numerator limit and the denominator limits separately. We know that 3 over x will go towards 0 as x goes to infinity. And then we have to think about these other ones here. So we know negative 1 is going to remain negative 1, and x plus 1 we can look at as a whole if we want. X plus 1 is going to go towards infinity, right? So hopefully that's pretty obvious. X plus 1 is going to go towards infinity as x goes towards infinity, and negative 1 is going to stay at negative 1. I'll write it like this so it looks a little better. I'll write 3 over x minus 1, so that's the whole denominator. That's going to approach 0 minus 1, so negative 1, as x goes towards infinity. So what you want to think of is you want to think of the answer as being negative or infinity over negative 1, which would equal negative infinity. But once again, you can't really write infinity over -1. Just kind of maybe write it on the side or think about it logically. Infinity divided by -1 would be negative infinity. Okay, so that is infinity as x goes to infinity with limits. So just be careful, never actually plug them in. And a lot of the times we just kind of have to remember some rules and think about them logically.